This is the 3D Pod, your number one source for 3D printing news, analysis, and insight from 3dprint.com. Now, here are your hosts, Joris Peels and Maxwell Bogue.
Hello everyone, my name is Joris Peels, and this is another episode of the 3D Pod. And with me, as always, is Maxwell Bogue. Hi, Max.
Hey, Joris, how you doing?
I'm good. How are you?
I'm fine, thanks. Anything fun and new going on with you?
Nothing. I went to my sister's wedding, so that was a big thing. And then after that, went to Holland and stuff, and now I'm back in Spain. So everything's going well.
Oh, look at you traveling around.
Yeah.
And who do we have on the 3D Pod today?
Well, we've got Charles Bibas today. Charles is really interesting because he spent a long time doing completely unrelated stuff than 3D printing, and ended up now coming up with a different kind of powder bed fusion technology. So first off, he worked on advanced barcode technology for a very long time, and then decided to found Tecnica. And he's been working on that for 8 years, or nearly even 9 years. And essentially, the optics on lasers are either like you work at a galvo, there's different ways of doing it, of course. And Charles has come up with a new way of doing it, where he has essentially a rotating laser that is meant to kind of reflect, a truer beam path in a completely different way, an Ogon laser or something like that. And it's one of these startlingly original ideas. And Charles is working on that. So welcome to the 3D Pod, Charles.
Oh, thank you for having me.
So first off, tell me a little bit about, before you were working in barcodes, it's something completely different, right? There are lasers in barcodes, right? So I understand.
That's true, scanning, yeah. So let's talk barcodes.
Yeah.
Do you like the QR codes? Or?
Yes, well, barcode scanning, laser scanning, it's much simplest form. Back in the day, Jerome Schwartz from Symbol Technology came up with a patent where he sent a laser beam to a surface. The surface reflected the beam. You collect the beam with a sensor, and then you can distinguish between a space and a bar, which is dark and spaces, and that's how barcoding made itself into the industry. The same technique, I dealt with that for many years with handling the scanning and the analyzing the algorithms to decode the barcoding. But I've seen there is that he used a scanner, a mirror scanner that basically it's rotating, oscillating from side to side, and send the beam to the surface and then collect the beam back. Mm-hmm. So that's my experience, which is in a nutshell not much with regards to optics, just the mechanism, and I was more on the side of designing the algorithms and the software to decode that barcode and bring it into a form that can be used for scanning. So that's the background with regard to barcoding and optics. You mentioned Advanced Barcode Technology. Advanced Barcode Technology is a company that I formed for the purpose of doing automatic identification solutions, in addition to also process control. And the two together, with the two pieces together, we were able to provide clients with solutions that composed of hardware and software.
And then what made you end up in 3D printing then? Were you just curious, or?
At some point in time, we needed an enclosure for one of our products. And that was in 2013. So the need was there. And we had some difficulties to find the proper enclosure because it needed to be IP65. And so I could not just put a simple enclosure there. And there where we ended up in a trade show in Chicago, looking into the different machines and companies. And that's where I realized that there is something missing. We see these big machines. And when I'm talking about machines or 3D in this podcast, we are talking about SLM, SLS, Selective Laser Sintering or Selective Laser Melting. And I've seen that those machines are very big and the print is very small. So something did not go right with the optics. So basically we made a decision, my partner and I, that we are stepping into this because we saw the opportunity. We got our enclosure and we saw the potential. And we decided that based on what we have done in the past, that we can help this market and bring this product to the masses and even simplify the product. That's the background to how we got into 3D.
I'm curious, was it almost instant that it hit you that this was like a problem when you saw the machines for the first time? Or was it not till you really started looking into them that you realized that this could be done in a much more effective and efficient way?
I have not seen that at the beginning. I did not even know what a galvanometer is. I just saw a big machine and I saw a small print. That's it. That was the beginning.
That's the problem.
Yeah. So so I scratched my head and I said, "Wait, why is that? Why a CNC can create a part relatively larger and an additive manufacturing machine cannot do the same?" And that's where we started to look into that.
And because galvanometers come from smoke machines, right? And so somebody decided at one point to use a smoke machine component to drive a 3D printer. I think that's even more strange, I think. So when did you decide to come up with a different kind of laser thing? Why did you decide not to go with Galvo? When did you decide was that from the beginning already that you decided to go with a different type of laser? Was that, why is that?
The objective was to build a new machine. The smaller, better. We did not know how it's going to happen. We had the objective. In the process, I came across the galvanometer, and I said, "1 second, what is that? Where we get information? How accurate is this? What's the baseline?" And then, as you said, it was used for entertainment to some level. It's used for scanning. And then it was adapted for writing. So we call that reading and writing. So when you read something with the galvanometer, you are basically seeking to get some information from where the galvanometer, where the beam is. When you are writing, you're doing the reverse. You send the beam and then you write into that specific location. Although they are symmetrical in nature, the beam going or the beam coming back, but the results are quite different when you analyze the end results, what you are expecting in writing and what you are getting in sensing. And that's where I realized that there is something here that may need to be corrected.
Okay. Because for those maybe unfamiliar, a galvanometer, essentially, it sounds really fancy, but it's like it's the same component, by the way, in the Formlabs printers or early Formlabs printers, and it's a mirror on a swivel mount. I mean, I'm overly simplifying it, but that's kind of like what it does, right?
But in a controlled way, right?
Yeah.
Like you can.
Well, if I describe it like in general, what I've seen from defining a galvanometer is that you have a beam that's rotating, and the focus is on a sphere. It's not on a flat area, and it's not on a flat plane. And because the beam is focusing on a sphere, in order to achieve the maximum performance from a galvanometer, you need to print on a sphere. That's the basic issue that I had looking into the galvanometer. So what the industry has done, they start to patch the galvanometer by flattening that sphere. And one way to flatten that sphere is just make the radius very large, and then the large radius will be considered kind of flattening the field. And that's why, by the way, the printers they are large because you are keeping that distance from the optics all the way to the print bed. So that was the initial observation that we have with the product. From our point of view, we looked at that and say, 1 second, that we don't want to put patches into the process, especially because when that beam is rotating and the beam is sintering or printing, then what's happening really is that the speed of the beam is changing on the print surface, even if the rotation is in a constant speed. So now you have another variable that is changing. The beam speed is changing. Because the beam speed is changing, also the energy deposited is changing. So that's one other parameter that we saw that is problematic. The industry came up with a solution that is a special lens that changed the speed to be more constant, and they use what is called an F-theta lens. And when you put that lens between the galv and the print surface, that speed becomes constant. So and there are other functions that you can add to this, because that's not the only problem that you have with galvanometer. The second problem that you have, it's called telecentricity, which means that as you move the beam, the angle of the beam with the surface always changing. And if the angle is changing, then also the beam size is changing. Also, the energy absorbed is changing. So we have few parameters that are changing with the standard galv. And the way it's handled nowadays, there are three functions that goes into that special lens, that you need a special lens that gives you three functions. One is to flatten the surface, the spherical surface. The second is to make sure that the telecentricity is much close to normal. And the third is to keep the spin constant. So all of these together are embedded into one lens that composes of many, many lenses in the structure. And that's costing in many trades-off. And that's, by the way, why you see different companies coming up with different systems and you have difficulties to compare. So that's what we have basically noticed for when we start to open that black box that's called galvanometer.
And I love this. So what did you do to change this? What was your innovation then, or one of your innovations then in trying to solve this problem?
Well, I went back to basic. The basic is we are printing on a flat surface. I want to be focused on a flat surface. Let's get this objective done. So that's how I start thinking.
Okay, go on, yeah.
And then I start thinking about optics. I also looked into the galvanometer. Another problem that I had with the galvanometer is it oscillates. It's not rotating, it's oscillating, which means accelerating and deaccelerating, going back and forth with that mirror. So you have wear and tear, and mechanically it's not a stable device that can be used for a long time. I came from the electronic industry, and in electronics, the parts, the ICs have much longer lifespan. And when you deal with mechanical system, usually they have shorter lifespan. So I did not like that piece, and that's another piece that I wanted to change. So I started from zero. I wanted to flatten the surface where the focus goes. And that's how I came up with the structure that composed of two mirrors only one mirror rotating, and the second mirror is just reflecting back to the surface. So by definition, this structure optically delivers a focus beam to the surface. The structure is simple. However, the smart is in the mirrors themselves, because now we do not have lenses. The function of the focusing is made by the two mirrors, by the first rotating mirror and also by second mirror. And that, I would say, the smart that went into this invention is the ability to focus the beam only by mirrors.
Okay. I think it blew me away when I first saw it, by the way. When I first I heard about this and read up on it, I was like, one thing, it's super ingenious, wonderfully done. And also it's like, really, the guys at ScanLab, all these other guys didn't come up with this? It's like, it's insane. It's insane.
No, that was my fear. When I realized that is as simple. It's a simple solution. It's only two mirrors, and it's giving you enormous speeds, because the speed now is dictated by the distance between the two mirrors. The larger that distance, the higher the speed. So there were so many advantages that I was always worried that my patent is not going to be granted on time, and that somebody probably filed for that. That was my main worry. So, yeah,
I know that.
I love it. It's like, are you sure? Are you guys sure? Because it seems really obvious. Okay.
I mean, I get also though. It's obvious for you coming from having done laser scanners, where I assume, a supermarket scanner, for example, barcode scanner, the mirror just constantly rotates. So you aren't having, as you described, that problem of slowing down and speeding up as you go left and right. You're just rotating and then scanning out. It's in some ways, it seems like you just took that and reapplied it to this to great effect. Is that?
Yeah, that's a good point, because really the USPTO, the United States Patent Office, really came up with that exact example that you mentioned. That they say, "Oh, your invention is very similar to this guy that made this barcode," and basically, and that was interesting, because I looked at that. I did not know it was patented, but when I looked into that closely, then I realized that that what they've done is they use a polygon, which means now you have few walls that project the beams. They did not care about focus as much because with barcoding you scan many scans and you hope that one of them will pick up the right pattern. But the issue with that system is that the distance between the beam source to the work surface is always changing. Our system, the distance from the beam source to the work surface is always constant because we design it this way. And that's the main distinction between barcoding to this system.
Okay. And what does that even mean? Okay, so I think it's a really beautiful thing from a pure innovation standpoint, right? So there's a length of the lifespan of the component. That seems good. What are the actual practical differences between doing this? You said you want a smaller system, maybe more accurate. What are the actual differences that you can do, day to day?
First, the distance between the optics to the workspace is controllable. We can put into the design any distance that we want. Specifically, if we talking about the CASA 2, where we implemented the design, the distance is about 70 millimeters. So now we have a distance between the optics to the workspace of 70 millimeters. This is an advantage. Compare this to a 500 millimeter or more that the industry is using. So now you are talking about a printer that it's a desktop printer. It doesn't have to take half of a room. So that's one advantage. The second advantage that we have is the environmental advantage. The print chamber, because the way how we print, our print chamber has only 11 millimeter high. It's only 11 millimeter height. And because of that, we can regulate the temperature in this chamber much easier than if you take 500 millimeter high chamber. So that's right off the bat. If you look at the machine, it does have these environmental properties and it's much more closer to what my objective was, to make a machine that print a relatively larger print than the small print that you get with a standard technology.
The way it's supposed to be. So you started all this, you saw this in 2013, and then you reached your first patent in 2016, 2017?
I believe 2015, 2016, the patent was granted in 2016, I believe. And then we follow up with more patents.
But then you started, when was your first prototype and proof of concept introduced to the world?
Well, I would say not to the world, to us. The way how I work is it's not a typical startup. If you take a look, usually a startup come with an idea, with PowerPoint presentation, and then the product will follow. I did work a bit differently with this because of the patents, and I kept everything in low profile until about a year ago. When we have done this, basically we follow the idea that, okay, we can if I can create this mirror, then a lot of products can follow, and different vertical markets can benefit from that. And so therefore I said I want a good proof of concept. I did not feel comfortable having other companies looking into this and trying to build a proof of concept. Also from an investment point of view, if you are seeking investment, then you need to bring the proof of concept already to the table. And that's what we have done. We went through stages. We did 3 prototypes. The very first prototype was to prove the concept that a beam can be moved in constant speed, that the mechanics work very well without the focusing. And then in 2018, in May of 2018, we had our prototype where we printed in 2D and 3D, and we confirmed the accuracy of the system. And that was within the limitation of what we had. And that was like a big moment, because at that time we confirmed that the beam is moving with the same focus constantly with the optics that we designed for that, and that we basically order optics, we put it together, and wow, we got the focus. And that was a big moment.
When did you guys decide to show the world that you had this amazing new, better way of doing SLS?
Well, it just started a few years ago when we realized that the patents has been accepted not only in the US but in many other countries. And we have 3 patents in China, we have 3 patents in Israel, we have 3 patents in Brazil. So we have patents all across the globe. But beside the patents, I would take it an extra step. When we did the design, we also had to design the electronics around that. So from IP point of view, it's not only the optics, it's what makes the optics run. And at that time, we could not find a laser that is fast enough to accommodate our scanner. So we designed our own modulator for laser. As in a comparison, for instance, if you take a modulator, a scanner now, it's limited to 5,000 hertz, which is about 5,000 pixels per second, and some may claim that they can deliver 50,000 per second. Our scanner is capable of 250,000 pixels per second. So that's a huge difference. And there are more advantages to the system, and the show is too short for that. But if you like, I can go there as well.
A little bit higher level. I mean, I understand first you're like, okay, you're self-funding this completely, right? So it's not a standard startup where you're doing it before, right? So, but then, aren't you going very far into the woods of making the system before actually having something on the market or having something to, how does that work?
Well, I would call this passion first. I have a passion for what I do. So the business objective, as for other companies, is get this to market. Let's start to distribute this. We are thinking differently. Of course, we like to do that, but that will require a lot of capital. And so what we do is we do what feels right for us, which is growing naturally and in small steps. However, with the right partner, we'll do that. If we have the right partner, we'll go and bring the product quickly to the companies that can use it.
And how far along are you right now? So you said a little bit about where you are right now, but what can you do right now in the demonstration units you have, let's say?
What we have right now is a printer, and that can print in 2D and 3Ds, and we are ready to pilot it. What we are working on is to have also this printer being available for the masses within 3 months.
And what is that then? Because I didn't know that. So what's that? What's that? Tell us more about that.
Again, we are a technology company. We develop something that we believe is great, and we like to make it available. And one way to do this is to build a printer. So we built a printer, and now that this printer will be ready for the consumers to use. I would say that we open also the door for a consumer. So now it doesn't have to go to business because of the size of the printer. You can, it's UPSable. You can have it in your garage. So that's open a whole new market.
And how do you hope to put this on the market? Because that, of course, would require an additional investment as well. Are you looking for partners for that, or do you want to self-fund that as well? Or
of course, we like to collaborate with companies. A, to make this technology accessible, and B, to have the product out there. With the right partner, we like to work with the right partners, and we are welcoming partners. At the moment, even we discuss solutions with certain companies. Some companies, come to us and say, okay, can you replace the whole Gulf system with your system while using our printer, the existing printer? Technically, it's possible, but I believe that it can go in 2 ways. One is the OEM avenue, which we are looking at, and the other is the avenue where we're selling the printers. With regards to OEM, I think that the potential is there, because if you take as an example, you can take our printer, which, by the way, it's portable. Which means, because of the distinction, when we print the arc, later on we move the actuator. So there is, it cannot be disturbed by movement. And if it cannot, then you can put the printed on a robot with a reach of about 1 meter or 2 meters. A robot has a repeating error of 50 micron. And then you can create stripes of prints and end up with a 100 micrometer repeating error print in a size of a meter. So that's one OEM application that I can see happen.
That's cool.
That would be amazing, and also very difficult to do, of course, with the heated chamber and the recoding and all this stuff. And
all that.
But again, that would be very exciting. And I think do you see, like, what are the kind of yields you're getting, or how fast is it? I know this is a really silly question because all these printers work very differently. There's no real, we don't have a megapixel, but give us a little bit of idea how productive the system is when compared to, like, the P110s that we all know and love.
The way how I gauge this is basically looking at the baseline, and that's how I've done when we started. A galvanometer has a limit in the speed movement, but also there are limits within the process. When we look into the theoretical limits, how fast you can run a galv and how much you can run our system, the ratio is about 65 times. We are much faster by at least 65 times. That's the capability of the system. The specific system, the CASA 2, we implemented a lower speed than that. If we are talking about the first unit will be comparable to the fastest printer out there in the market. However, the capability is there to deliver 65 times faster print. And because I mentioned the process, there is another thing that's happening here. Because the present system is dealing with limitation in the print, the process was defined with some limitation. For example, when you print a metal, you are creating hatches, and you design the print so you will have enough conductivity that it's sufficient not to burn the metal, just in a nutshell. And the piece that the industry is worrying about or dealing with is that beam that I was talking about, changing the angle every time. And it doesn't make a difference how many patches you put in there. You are going to get a change of the angle. If the beam angle is changing, the energy that radiating or that moving in conductivity in the metal can move in two directions. Either energy is displaced in the lateral direction or the vertical direction. And those two displacement vectors are changing as you move the beam. So now you have a moving target that you need to adapt for each pixel, each voxel that you are going to print. In our system, we don't have it. What we have a vertical beam that goes always down. So all of the energy is always going in one direction. And because of that, we reduce the number of parameters when it comes to dealing with energy consistency in the process of printing a whole metal layer, for instance. So what I'm trying to say is that we created a new environment that will be redefining the process how you do 3D printing with metals.
It's nice for you to keep this close to the chest. It's nice for you to say this is a hobby thing and I'm going to work on developing the technology. But you have said it before, you will require an enormous amount of money to do this. I mean, I think, wouldn't it be better to just license this to another company and go on inventing or something like that? Wouldn't that just be a way forward? Or do you really feel like going further into different platforms and different systems is the way forward?
It's not a baby that that I have a direction for it. So whatever help the industry, whatever is good for collaboration, I'll do. I'll follow the best path that will bring this to market, and it's based on the VCs and the strategy they want to go with. The potential is there, and I'm listening.
And are there also advantages, I think, because the printhead works on both, for metals and polymers and stuff like that, right? And presumably also ceramics and stuff like that. But, are there intrinsic advantages to on metals as well? You said as well that the directionality could be an issue. Is it also, could you make less stress on the metal part, for example? Are you seeing less deformation, for example, stuff like that?
I believe yes, because again, it's in my opinion, we did not test metal yet, but based on the theory, based on the way how it's function, we are reducing the number of parameters, and therefore the stress is going to be the causes for stress, the number of parameters that cause to that stress are reduced. And by reducing them, we have a much more easier system to control. And that's right off the bat what I can say about our system and printing metal. Other piece that I will add to this is that one of the issues with metal printing now is that the beam that is used by the industry is a Gaussian beam, which means that the beam at the center is very, very, very small, and then the energy start to decrease as you get away from the center of the beam. This model is not great for metal printing because when you print metal, you are required by definition to have a higher heat conductivity by the metal. And if you don't have it, you are going to puncture the metal. One advantage that we have, because we don't use Gaussian beam, so we use a flat beam, and because of that, the energy is all distributed at the print area. And I believe that this system will be more forgiving for certain powder that their heat conductivity is not going to be so high. So I believe it can open market for more powder in the field of metal.
Yeah, or metals that are like refractories, or metals that have been a bit more complicated for us, like so far maybe. That could be very exciting. And how have you been doing this? Because I think it's really fun to see tinkering. I could imagine you tinkering your own lab kind of thing. But at one point, to a certain extent, but at one point it gets really complicated, right? You have to drag in lots more people, right?
Oh, absolutely. That's the key word. I could not do this by myself. Absolutely. When I started with this, I started, of course, with a patent. I had a company that I was running. It was paying the bills. And I start using the engineers that I have on the company already to help with the process. If it's to build a prototype, if it's to design the first mirrors, to send the mirrors for production, there is a lot involved. I think that my work in general, me personally, was in designing the mirrors. It took me more than a year to study ray tracing and to come up with the mirror. I did not want to do it, just to give you an idea. I knew what I wanted. No, seriously, because I'm not an optical engineer. Let's start with this. So I'm not an optical engineer. I'm a fond believer that you better do what you are good at. So, and that's what I was trying to do. So I had no other choice. I subcontracted about 6 optics experts in the field to make for me the mirrors, and I did not get good results at all. So I had no other choice but to study optics. I knew there is a solution, and that's the great part about it. I knew there is a solution, and I believe that because I was an outsider to the optical field, I was able to come up with a solution. And here is why. An optic engineer will look into optics and into an image and say, I want to image that thing. I want to keep that image as is. I myself did not look at that this way. I did not look at the image and say, I want the same image to end up. I don't care. I want a dot. I want a focus. So I don't care if that focus is going to change the image, because by the end of the day, you render a picture with many dots. So the dot doesn't have to be an image by itself. I don't know if that makes sense. And because I thought this way, I was able to come up with mirror formulas that will get me that very specific small dot that I was after. And that's I would say that was my biggest thing out of everything. That's what I got. That's my accolades from my point of view.
But I like the idea that. But so, what made you continue? Because like up until now, I thought this was like a super fun project for you to do, and then you kind of were very passionate. One of those like the people that just solve something. But so you're telling me this was not fun?
It is fun. It's fun. It's fun. It's a different fun now. You mentioned the people. I could not do this without the people that I have in my team. And I have people that are working remotely on this. I have a great embedded engineer. I have a great FPGA engineer. Because bear in mind, if you cannot use a standard PLC for this. PLC is not a real-time system that can react in micro or nanosecond. So we created a system that interact within the micros and nanoseconds with the optics. And that's why we have the ability to modulate the laser in very high speed. So these people made it. So I would say along the years, we had about 2,000 engineers involved in this project in different aspects of the project.
Yeah, I think it's wonderful. I think it's a wonderful story. But I think also we saw this before with certain technology. If you're doing something a little bit different, then the go-to market is really the challenging thing. So if you're looking forward, now you're at the cusp of maybe commercializing this thing. What do you hope to achieve in the next 5 years, let's say?
I want to see the printer deployed with a lot of collaboration. I believe that the mentality of black box should not be followed, like the industry is following the black box mentality when it comes to galvanometer. So everybody try to fix something, and therefore there is an issue with regard to a universal way of representing something. And to be clear on this is each printer out there, if you want to validate the print, you need to validate the print itself and the process. We are talking here about a new market. Additive manufacturing has additional complexity if you compare it to subtractive manufacturing. In subtractive manufacturing, you get a raw material where the microstructure is well defined. Additive manufacturing, you are going from powder, which is solid, then to a liquid and back to solid. So the microstructure has been modified by the additive manufacturing. And if you want to qualify your parts, then you need to address this piece. Each printer nowadays is creating a different microstructure, even within the printer itself. If you place the part in different parts of the print bed, you get different microstructure for the print. So I would say that I like to see that a more universal way of communicating in this market, where we put some universal standards, even the way how the part is defined, in a way that you can go back and keep an audit trail with what you have done and what you wanted to do.
Yeah, that could be really, really very exciting. Okay. Well, thank you so much. This is a really fascinating story. I think really, really kind of like steadfastly trying to develop this with this small team. I think it's absolutely fantastic, and I hope we see a lot more of this because I think it's really wonderful what you guys are doing.
Oh, thank you. Thank you for having me.
I'd love to have you back on the show and hear where it goes from here.
Yeah, I think we're really.
I want to know what's going to happen.
Yeah, I think we're very excited. I think we're very excited to see how that would go. And so thank you, and thank you for being here today with Max as well.
Always, yeah, fascinating.
And thank you for listening. This is another episode of the 3D Pod. My name is Joris Peels. Have a great day.
You've been listening to the 3D Pod. For more information on what you just heard or to subscribe, visit www.3dprint.com or follow us at 3dprint_com.